Right now, as you're watching this video, our sun has just unleashed something powerful. Just hours ago, on December 4th, a massive M60 class solar flare erupted from the sun's surface. And here's the shocking part. It came from a sunspot that didn't even exist. NASA's satellites captured it in real time, and scientists are scrambling to figure out if this monster is heading straight for Earth. The sun has delivered another major outburst. Just hours into December 4, a newly emerged sunspot region designated AR4300 unleashed a strong M60 class solar flare. This marks one of the most significant eruptions from a brand new active region rotating into Earth-facing position this solar cycle. NASA's Solar Dynamics Observatory captured the flare in real time, recording intense extreme ultraviolet radiation bursting from the sun's southeastern limb. The U.S. Air Force Space Weather Division simultaneously detected a Type 2 solar radio burst at the exact moment of the flare, indicating shock waves moving through the sun's corona. This signature typically means a coronal mass ejection has been launched into space. NOAA Space Weather Prediction Center is currently analyzing coronagraph imagery to determine the speed, direction, and Earth impact potential of this CME. This is happening now. What makes this flare particularly notable is its source. Sunspot region 4300 was not visible on the Earth facing solar disk until December 2. Within 48 hours of rotating into view, this region produced a substantial M60 class flare with likely CME generation. The rapid activation of AR4300 demonstrates how quickly solar active regions can develop explosive potential. Scientists at the NOAA Space Weather Prediction Center are monitoring this region closely as it continues rotating towards center disposition over the next several days. Scientists are actively tracking this development because AR4300 adds another active region to an already volatile solar environment. The sun produced an X19 class flare on November 30 from a different active region. That eruption generated a CME, but trajectory analysis showed the plasma cloud would miss Earth. Now, just 4 days later, a completely separate region has erupted with significant force. Here's why that matters. The December 4 M60 flare registered on the geosatellite X-ray flux monitors maintained by NOAA. M-class flares are the second strongest category in the solar flare classification system, which ranks eruptions by X-ray intensity. The scale progresses from A, B, C, M to X, with each letter representing a T-fold increase in energy output. Within each class, numbers provide further gradation. An M60 flare releases approximately 60% of the energy of an X10 flare. While not in the most extreme category, M60 events carry substantial energy and can trigger measurable space weather effects. The Type 2 radio burst detected by the U.S. Air Force confirms shockwave propagation through the solar corona. These radio emissions occur when accelerated electrons generate plasma oscillations at twice the local plasma frequency. Type 2 bursts specifically indicate a shock front moving outward from the flare site, compressing and heating coronal plasma. This signature provides direct evidence of a CME in progress, even before coronagraph instruments can visually confirm the plasma cloud. Current observations reveal AR4300 occupies coordinates approximately S2045 as of December 4. This places the region in the sun's southern hemisphere 45 degrees east of the central meridian from Earth's perspective. The E designation means the region is still on the sun's eastern limb relative to Earth, continuing to rotate into more direct alignment with our planet. Over the next 5 to 7 days, AR4300 will traverse center disk, the zone where any eruptions have maximum Earth impact potential. What this means for near-term space weather is significant. If AR4300 maintains its eruptive activity while positioned at center disk, any subsequent CME launches would likely be directed toward Earth. The region's magnetic field configuration is still being analyzed. Scientists use magnetogram data from the Solar Dynamics Observatory's helioismic and magnetic imager instrument to map active region magnetic topology. Complex magnetic structures particularly those with delta configurations where opposite magnetic polarities occupy the same penumbral area, correlate with higher flare probability. Space weather. Com reported the M60 flare within hours of occurrence, noting the preliminary CME detection based on radio burst data. The site's analysis indicated the CME, if confirmed, would require further coronagraph imagery to establish the trajectory. NASA's Solar and Heliospheric Observatory and NASA's Solar Terrestrial Relations Observatory provide coronagraph views that block the sun's bright disk, allowing faint coronal mass ejections to be photographed against the background of space. These images typically become available several hours after a flare as data downloads from the spacecraft. Think about that. The timing of AR-4300's emergence adds to existing uncertainty in the space weather forecasting community. Predicting when new active regions will rotate into view presents inherent challenges. Sunspots form in the solar convection zone. Approximately 200,000 kilometers below the photosphere, magnetic flux tubes rise through this turbulent plasma environment, eventually breaking through the visible surface. Helioseismology techniques can sometimes detect active regions before they emerge by tracking subsurface plasma flows and magnetic concentrations. But this capability remains limited. The Helioseismic and Magnetic Imager on NASA's Solar Dynamics Observatory provides far-side imaging through seismic wave analysis. When solar oscillations propagate through the sun's interior, they are modified by magnetic structures on the far side. By measuring changes in oscillation patterns on the Earth-facing side, scientists can infer the presence of active regions approximately 7 to 10 days before they rotate into direct view. However, this technique cannot predict eruption timing or intensity with precision. AR-4300 may have been detected in far-side data, but forecasters could not have determined it would produce a major flare within 48 hours of becoming visible. This raises important questions about the limits of current forecasting capabilities. Space weather prediction relies on real-time monitoring of visible solar features combined with statistical models of active region evolution. Unlike terrestrial weather, where atmospheric data can be collected globally and continuously, solar forecasters can only observe one hemisphere of the sun directly. The sun's 27-day rotation period means active regions spend approximately 13 to 14 days on the visible disk before rotating onto the far side. Any region can develop or decay significantly during that period out of direct observation. The debate about forecasting accuracy intensified on social media platforms following the December 4 fair. Several space weather enthusiasts questioned why NOAA and other agencies did not issue advanced warnings about AR-4300's potential. Some users suggested that the sudden eruption indicated a failure in monitoring or analysis. However, professional space weather forecasters emphasize the inherent unpredictability of solar active region behavior. Even well-established sunspot groups can remain quiet for days before suddenly erupting, while others decay without producing significant flares. NOAA Space Weather Prediction Center issues daily space weather forecasts based on current active region characteristics. These forecasts assign probabilities for C, M, and X-class flares over the next 24 hours and 3 days. Probabilities are derived from active region magnetic classifications, historical eruption rates for similar configurations, and recent activity trends. As of December 3, before the M60 flare, forecasters likely assign moderate probabilities for M-class activity based on the presence of multiple active regions, but could not specifically predict AR-4300's behavior with only 1 day of observational data. The controversy highlights a persistent tension in space weather communication. Forecasters must balance precision with honesty about uncertainty. Overstating prediction confidence can lead to complacency when forecasts appear inaccurate. Understating risk can leave satellite operators and other stakeholders unprepared for significant events. NOAA's approach emphasizes probabilistic forecasts that acknowledge inherent uncertainty while providing actionable guidance based on current conditions. The M60 flare from AR-4300 produced an immediate radio blackout on the sunlit side of Earth. When solar flares erupt, they emit intense bursts of X-rays and extreme ultraviolet radiation that reach Earth in approximately 8 minutes, traveling at the speed of light. This radiation ionizes the upper atmosphere, particularly the D region of the ionosphere, at altitudes between 60 and 90 kilometers. Enhanced ionization increases radio wave absorption, degrading or blocking high-frequency radio communication. The NOAA Space Weather Prediction Center reported an R2-level radio blackout associated with the December 4 flare. On the R scale for radio blackouts, R2 represents moderate impacts. High-frequency radio communication can experience degraded performance or a complete loss of contact on sunlit portions of Earth for tens of minutes. Aviation, maritime, and amateur radio operators relying on EHF bands between 3 and 30 MHz are most affected. The blackout began at 2:50 and lasted approximately 30 to 45 minutes as the FLAR's X-ray flux declined back to background levels. Building on this, scientists are now focusing on the potential CME associated with the flare. Coronal mass ejections represent far more significant space weather threats than the flares themselves. While flares cause immediate radio blackouts, CMEs transport billions of tons of magnetized solar plasma into space. If a CME reaches Earth, it compresses the planet's magnetosphere, triggering geomagnetic storms that can disrupt power grids, satellite operations, navigation systems, and communications infrastructure. The Type 2 radio burst detected on December 4 strongly suggests that a CME accompanied the M60 flare. However, confirmation requires coronagraph imagery. NASA's Solar and Heliospheric Observatory, positioned at the first Lange point between Earth and the Sun, carries the Large Angle and Spectrometric Coronagraph instrument. This device photographs the Sun's corona out to approximately 30 solar radii, capturing CME structures as they propagate through the inner heliosphere. NASA's Twin Solar Terrestrial Relations Observatory spacecraft provides side-angle views, allowing three-dimensional reconstruction of CME geometry and trajectory. As of December 4, analysts are processing coronagraph data to determine whether the CME is Earth-directed, partially directed, or directed away from Earth. The location of AR-4300 at S20E45 suggests any CME would initially be directed somewhat eastward from the Sun-Earth line. However, CMEs often expand laterally as they propagate, and even eruptions from off-center locations can deliver glancing blows to Earth's magnetosphere. The November 30X19 flare originated from a different position and produced a CME that ultimately missed Earth. Each eruption must be analyzed individually based on its source location and the CME's three-dimensional structure. Let that sink in. The December 4 flare measured M60 at its peak intensity. This classification is based on X-ray flux measured in the 1 to 8 angstrom wavelength band by NOAA's geostationary operational environmental satellites. The GEO-16 and GEO-7 satellites continuously monitor solar X-ray output, providing real-time data to forecasters. An M60 flare corresponds to an X-ray flux of 6×10⁵ watts per square meter at Earth's orbit. For comparison, an X10 flare measures 1×10⁴ watts per square meter, meaning the M60 event released approximately 60% of that energy. The Solar Dynamics Observatory captured detailed imagery of the flare in multiple extreme ultraviolet wavelengths. SDO's Atmospheric Imaging Assembly instrument images the Sun every 12 seconds and 10 wavelengths, each corresponding to different plasma temperatures. The 131 angstrom channel, sensitive to material heated to approximately 10 million degrees C, shows the brightest flare emission. The 171 angstrom channel, capturing material at 600,000 degrees C, reveals cooler coronal loops and structure surrounding the flare site. By analyzing these images, scientists can determine the flare's magnetic topology and energy release mechanism. Solar flares occur when magnetic energy stored in the Sun's corona undergoes rapid release through a process called magnetic reconnection. Active regions contain complex magnetic field structures where field lines of opposite polarity converge. Under certain conditions, these field lines break and reconnect in a lower energy configuration, converting magnetic energy into kinetic energy, heat and particle acceleration. Electrons and ions are accelerated to relativistic speeds, producing the X-ray and extreme ultraviolet emission that defines the flare. The magnetic configuration of AR4300 is still being evaluated. Early magnetogram data from December 3 and December 4 show a bipolar sunspot group with significant magnetic flux concentrated in relatively small areas. High magnetic flux gradients increase the probability of reconnection events. Scientists are specifically looking for signs of magnetic shear where field lines are twisted relative to the potential field configuration, and magnetic emergence where new flux continues rising through the photosphere. Both characteristics indicate stored energy available for flare production. What we're seeing now is that AR4300 continues to evolve. Sunspot regions typically develop over several days as magnetic flux emerges from below the photosphere. The visible sunspot represents the area where concentrated magnetic fields suppress convective heat transport, creating cooler, darker regions on the solar surface. The magnetic field strength in sunspot umber can exceed 3,000 gauss compared to the quiet sun's field strength of just a few gauss. As more flux emerges, the active region can grow in size and complexity, increasing its eruptive potential. The December 4 flare adds to an active period for solar activity. Solar cycle 25, which began in December 2019, is currently approaching its maximum phase, predicted to occur sometime between late 2024 and mid during solar maximum. The number of sunspots and active regions increases substantially, as does the frequency of flares and CMEs. The current activity level is consistent with an active solar maximum, though the sun's behavior remains difficult to predict in detail. This connects to longer-term patterns in space weather. Solar cycles typically last approximately 11 years, from one minimum to the next, driven by the periodic reversal of the sun's magnetic field. Cycle 25 has shown moderate intensity so far, neither particularly weak like cycle 24, nor exceptionally strong like cycle 19 in the 9 and 50 seconds. However, individual events during any cycle can be significant, and current activity demonstrates that impactful flares and CMEs continue to occur. The X19 flare on November 30 provides recent context for understanding AR4300's December 4 eruption. That earlier event originated from a different active region and produced a fast CME, but trajectory analysis confirmed it would miss Earth. The plasma cloud propagated into space away from the Sun-Earth line, illustrating that not all solar eruptions affect our planet. Space weather impacts depend critically on the precise alignment between the eruption site, the CME trajectory, and Earth's position in its orbit. Scientists at NOAA's Space Weather Prediction Center are currently running models to predict the potential arrival time of any Earth-directed CME from AR4300. These models use coronagraph observations to estimate the CME's initial speed and direction, then simulate its propagation through the solar wind. The Wang-Xiarge model and the WSAN model are standard tools for CME forecasting. These physics-based simulations account for the background solar wind structure and interactions between multiple CMEs, if present. CME transit times to Earth typically range from 15 to 18 hours for extremely fast events, exceeding 2,000 km per second, to 3 or 4 days for slower CMEs traveling at 300 to 500 km. The December 4 flare's intensity suggests a potentially fast CME, but confirmation requires coronagraph data. If the CME is partially Earth-directed and traveling at 800 to 1,200 km per second, a typical speed for significant eruptions. Arrival could occur between December 6th and December 8th. This leads to specific monitoring priorities over the next several days. Forecasters are watching for several key indicators. First, coronagraph imagery will confirm the CME and establish its trajectory. Second, measurements from NASA's Advanced Composition Explorer spacecraft and NOAA's Deep Space Climate Observatory, both positioned upstream of Earth at the first Lagrange point, will provide advanced warning when the CME arrives. These spacecraft monitor the solar wind continuously, detecting changes in magnetic field strength, plasma density, and particle velocity that signal an incoming CME. The geomagnetic storm potential from a CME depends on its magnetic field orientation. When a CME reaches Earth, it carries the sun's magnetic field frozen into the plasma. If the CME's magnetic field is oriented southward opposite to Earth's northward pointing magnetic field, reconnection occurs on the day-side magnetosphere. This allows solar wind energy to enter the magnetosphere, driving geomagnetic storms. Northward-oriented CME fields produce minimal geomagnetic activity because reconnection is suppressed. NOAA uses the KP&G scale indices to characterize geomagnetic storm intensity. The G scale ranges from G1 minor storms to G5 extreme storms. A fast Earth-directed CME with strong southward magnetic field components can produce G3 strong or G4 severe storms. These events cause widespread voltage control problems in power systems, trigger false alarms on protection devices, induce currents and pipelines, and degrade GPS accuracy. Auroral displays become visible at lower latitudes, sometimes reaching the northern United States during G4 events. The implications are significant for satellite operators and infrastructure managers. Geomagnetic storms increase atmospheric drag on satellites in low Earth orbit, accelerating orbital decay. Spacecraft charging events become more likely as high-energy particles penetrate satellite electronics. Communication and navigation systems experience degraded performance. Airlines reroute polar flights to avoid high-frequency communication blackouts and increase radiation exposure. Power grid operators implement mitigation procedures to protect transformers from geomagnetically induced currents. This is unprecedented in one specific sense: the rapid succession of significant solar events. The X-19 flare on November 30, and now the MT60 flare from newly emerged AR-4 on December 4 illustrates the sun's volatile behavior during solar maximum. While multiple eruptions over several days are not unusual, the involvement of different active regions and the quick activation of AR-4 demonstrate how dynamic the solar environment can be. Right now, scientists are also evaluating whether AR-4 might produce additional eruptions. The region remains visible on the solar disk and will continue rotating toward optimal Earth facing position over the next week. If the magnetic configuration continues to evolve, particularly if new flux emergence occurs or magnetic shear increases, the potential for further flares remains elevated. NOAA forecasters will update daily space weather predictions based on ongoing observations of AR-4's magnetic structure and any signs of increased activity. The U.S. Air Force Space Weather Division plays a critical role in monitoring and forecasting space weather events. Military satellite systems, communication networks, and navigation infrastructure are particularly vulnerable to space weather disruptions. The Radio Solar Telescope network operated by the Air Force provides continuous monitoring of solar radio emissions across multiple frequencies, detecting Type 2 and Type 4 radio bursts that indicate CME activity. This data complements optical observations from NASA and NOAA spacecraft, providing rapid confirmation of energetic solar events. As of this moment, coronagraph analysts are examining LASCO's C2 and C3 imagery from the Solar and Heliospheric Observatory to measure the CME's angular width, speed, and trajectory. The C2 coronagraph images the corona from 2.5 to 6 solar radii from the Sun's center, while C3 extends coverage from 3.7 to 30 solar radii. A CME appears as a bright expanding structure moving outward through these fields of view. By measuring the CME's leading edge position in successive images, analysts calculate its speed. By comparing its position relative to the background stars, they determine its trajectory in three-dimensional space. The latest analysis shows that AR-4300 occupies a compact area with multiple sunspots. Ground-based solar observatories and space-based instruments are tracking the region's evolution in real time. The National Solar Observatory operates facilities including the McMath Pier Solar Telescope and the Global Oscillation Network Group stations that provide continuous high-resolution observations. These facilities complement space-based assets, offering independent verification of active region characteristics. Current observations reveal that the sun's activity level remains elevated compared to the relatively quiet conditions during the recent solar minimum from 2018 to 2019. During that period, days without any visible sunspots were common. In contrast, December 2025 has seen multiple active regions simultaneously present on the visible solar disk. This increased activity level is expected to continue through 2025 and into 2026 as solar cycle 25 progresses through its maximum phase. Scientists are paying attention to the broader context of space weather monitoring capabilities. The fleet of spacecraft observing the sun includes NASA's Solar Dynamics Observatory in geosynchronous orbit, providing continuous high-resolution imaging. The Solar and Heliospheric Observatory at the L1 range point offers coronagraph and helioosmology instruments. The twin stereo spacecraft, though one is currently not operational, provide off-axis views of the sun. Ground-based observatories worldwide contribute optical, radio, and magnetic field measurements. This network of observing platforms enables comprehensive space weather monitoring, but gaps remain. The far side of the sun cannot be directly observed except through helioosmology, which provides limited information. The interval between a CME launch and its arrival at Earth gives forecasters lead time measured in hours to days. But precise prediction of geomagnetic storm intensity remains challenging because the critical parameter, the CME's magnetic field orientation, cannot be measured until the plasma cloud reaches upstream monitoring spacecraft just 30 to 60 minutes before Earth impact. Here's the key point. AR-4300's December 4 eruption underscores the dynamic nature of solar activity and the challenges inherent in space weather forecasting. The region emerged, developed, and produced a significant flare within a compressed time frame, limiting the advanced warning forecasters could provide. This pattern is typical of solar active regions, which can evolve rapidly and unpredictably. The question now is whether this CME will impact Earth and what effects might result. If coronagraph analysis confirms an Earth-directed trajectory, NOAA will issue CME alerts and geomagnetic storm watches. Satellite operators will review spacecraft health management procedures. Power grid operators will prepare for potential geomagnetically induced current mitigation. Airlines will monitor space weather updates for polar route decisions. Amateur radio operators and aurora watchers will prepare for possible high-latitude auroral activity. Over the next 48 to 72 hours, as coronagraph data is fully analyzed and propagation models are refined, the space weather forecasting community will have clearer answers about the Earth impact potential of the December 4 CME. In the meantime, AR-4300 remains under continuous observation. Any additional flare activity from this region will be immediately detected by the Solar Dynamics Observatory and GEO satellites, with updates issued by NOAA and reported by SpaceWeather.com and other space weather information sources. The December 4 event demonstrates that even as forecasting tools improve, the sun retains the capacity to surprise active regions emerge, evolve, and erupt on time scales that challenge prediction capabilities. Scientists continue working to improve space weather models, expand observational coverage, and refine understanding of the physical processes driving solar eruptions. Each significant event like the M60 flare from AR-4300 provides data that advances this effort. As of December 4, the sun remains active and unpredictable. Multiple sunspot regions are visible. Solar flare probabilities remain elevated, and the potential for additional CME launches continues as long as complex active regions occupy the Earth-facing solar disks. This is happening right now. The M60 flare from Sunspot region 4300, the Type 2 radio burst indicating a likely CME, and the ongoing analysis to determine Earth impact potential represent the reality of space weather in an active solar cycle.